Hi, I'm Federico, and I would like to start telling you what we do at ISO, and then I will pass the mic to Piotr that will go more in the technical details and how we use AlmaLinux and how we customize it. So what is ISO? We are the European Southern Observatory. We are an intergovernmental organization that provides facility for ground-based astronomy. Basically, we do telescopes. We provide the facilities, we run the facilities, but the proposals and the real science comes from outside, from universities, from consortia, and theoretically from whoever wants to do a proposal. So people do proposals or observations, they ask us with our instruments to look at something, the data is then there, and then they do whatever they think is good for the science. So this is an organization that was founded, as you see, in 1962, so pretty old organization. It's composed from 16 member states, most of the European Union countries, plus Chile, which offers us the places where we have the telescopes physically, and Australia, which is a special partner in the last years. Our headquarters are in Munich, so just north of Munich, out of the city. There is the photo from the top. You can see there the old building, technical building, when we have our data center, the new offices, and there is also a center, exposition center, which everybody can visit, see some planetariums, some very interesting images. On the other side, all the astronomical facilities are in Chile. Why Chile? First of all, because there is the Atacama Desert, which is one of the driest places on Earth, which means the best skies you can have on the planet to observe the skies. These are on the mountains. We are talking about over 2,000, 3,000 meters, and there is extremely dry and hardly rains. I mean, you have a couple of days of tiny, tiny rain over a year. So very dry places. You will see the photos later. The second motivation for Chile is that being on the southern hemisphere, you can see certain objects which you can't see, or you see very badly if you are on the northern part of the hemisphere, specifically the center of our galaxy. So you can see much more there. If you were ever on the southern part and in a dark sky, for sure you saw the big patch, which is our galaxy on top of your head. So a bit of history. The first observatory was in La Silla. This is in middle Chile somehow, not far from a city called La Serena, if some of you know Chile. And this is operational since '66. So you see, also in our case, our facilities are very long-lived. So a lot of years we support the same telescopes. And here, let's say the biggest telescope, which is 3.6 meters, is from '76. And it's still operational. There are about 10 telescopes still operational there. There are optical telescopes, radio telescopes, and so on. And we are still adding some of new instruments on them. No new telescope, let's say the telescope is, let's make it, to call it easy, the mirror that collects the lights. Then the instruments is something that gets these lights and does some scientific operations on it. So here we still produce a lot of science, even in 2019, not far from now, Nobel Prize came out from what is done here. And what is quite interesting here is that we get also a lot of local interests for astronomy and computing, which are various local animals, which are guanacos, vicuñas, which are more or less the Chilean version of the alpacas, and foxes, and so on. What is interesting, if you go to this side, on the road, you still see the poles of the telephone lines, because when all this started, all the scientific data was still sent with telex. Maybe many of you are quite young, never heard about it, or for sure never used the telex, but this was how it was working, and everything is still there just for the fun of it. Nobody's using, luckily. So the second facility is Paranal. It's called, from the mountain where it stands, it's called Cerro Paranal. You can see a photo of it. Don't be afraid, it's not burning. That is a photo from the James Bond movie. Actually, the observatory was also part of one of the James Bond movies, Quantum of Solace, where they filmed a lot of things inside the residencia, which is where the part where we sleep and so on at night. And the bad guys also had one of the UTs I don't know what they were doing sincerely, but okay, they were doing something with them in the movie, I don't recall it. So this is 4 telescopes. Each of them is 8 meters in diameter. So it may sound not so big, but it's very impressive when you see it. And besides these 8 meters, we have another 4 ones, which are roughly 2 meters. What is very interesting here is that these telescopes can also be used all together in what is called interferometry. So basically, you collect the lights from all the telescopes, you collect it together via a series of tunnels which are underneath the platform, and you collect it together at the exact same point, and you basically have a virtual equivalent of a telescope which is as big as the two that are further away. So basically, you have, instead of a telescope of 8 meters, you have a virtual telescope of around 40, 50, which is the distance between these. Why I'm telling this? Because this is a modern trend in astronomy. You may have heard there are many projects which put telescopes around the world and then try, of course, timing very precisely the observation to collect and unite the data to simulate, let's call it like this, a much bigger telescope. Also here, thanks to these technologies, there was a lot of Nobel Prizes in physics, one in 2020, for example, when it was demonstrated that in the center of the galaxy there is a black hole of our galaxy by observing how the objects are attracted and moving around a certain spot. Of course, you can't see the black hole directly, or at least you couldn't see the image directly. You just saw by how everything is rotating around it. Besides this, there are a few other telescopes which are done for surveying, so for scanning all the sky very fastly. In a couple of nights, you do the whole skies, you see if there is something particular, and based on this, you then program to go to observe more in detail certain events or something like that. Around Paranal, there will be soon also built the so-named Cherenkov telescope array. This is an array of very small radio antennas, but it's a huge number of radio antennas which are spread around a big area. And with the same concept that I said before about interferometry, you can then simulate something very big. Some of these telescopes will be in, let's say, in this site, some in other sites, and then together the data will be collected. The third observatory is called ALMA. This is a project which is done together with the North American and the Japanese, Taiwanese astronomical associations. This project, operational from 2011, is composed by 66 antennas, which can be moved on this plateau, which is at 5,000 meters, so very high. It's even hard when you go to work there. You have to use the oxygen mask and so on in some cases to work in these conditions. Also, the computers have to be specifically designed for being, let's say, working at these altitudes. What is interesting about these antennas, which looks pretty small here on the image, is that the dishes, 50 of them are 12 meters in diameter, so they're pretty big. The other ones are 7.5, 8 meters. And all these antennas can be moved around. Basically, these antennas can be collected in a range of around 150 meters up to 16 kilometers. They are moved around with some special trucks. And again, with the concept of interferometry, this data is then collected and simulated some very long baselines to be able to observe specific objects. It's interesting also that here we don't have a wireless radio or anything. This is fiber optic, which when you move the telescopes, you also pull cables to have everything in communication. This is also not to have delays, not to have problems of this kind on these very big distances, because on kilometers, even the speed of light has delays. This is also part of a bigger effort of interferometry, which is called the Event Horizon Telescopes. So sites around the world collect the data together, they unite it, and they can simulate even bigger telescope than this. On the top right is interesting, maybe you saw it in the news some years ago, is an image of a black hole in the center of the galaxy, done specifically with from this ALMA site. I mentioned here there is also Apex, which is just a single of this antenna, which is even higher, of 5,500, is the observatory highest in the world, has positioned highest in the world. and was a project which somehow kicked, was an experiment for then the future of ALMA. But now let's go to today, and what we want to talk more about today, and is the ELT. So the ELT stands for Extremely Large Telescope. So like in CERN also we are very good at naming. The other was very large, this is extremely large. Let's see the next one. And this telescope will be 39 meters in diameter. As I'm sure you all know, or at least you have to admit to know, when we talk about radius, if you do a mirror, let's say the area doesn't grow with R, so with the mirror, but with the square of it. So going from the 8-10 meters of today to 40 meters almost is a huge jump. There are another two projects of this dimension from the American colleagues, the TMT and the GMT. You may have heard, sadly at the moment they are stopped, but let's say this brings the ELT the responsibility to be the largest telescope on the first over 30 meters in the near future. So this is a photo of a year ago, approximately. Right now, I was there a month ago, is totally finished, the structure. So also the doors that here you see still just partially done are finished. We are just proceeding now to whatever has to be done inside, which is still a lot of work, for example, all the cabling and so on. But we are hoping to see the first light in 2029. So this is just 3 years from now. And starting next year, we are going to do what is called the verification there. So we start putting computers inside and everything else inside. So the point of this telescope is to observe exoplanet and things like that. Just to give you an idea what kind of science can be done with this, till now, whenever you hear about exoplanets, we never observe them directly. We just know that they are there, for example, because we see a star blinking and we know that something is passing in front of it and we can deduce that there is a planet there. We never image it directly. The ELT will be, thanks to this big mirror, the first one that will be able to do direct imaging of exoplanets. So you could see really a planet near some of the stars nearby. So the mirror is not a single 39 mirror, it would be extremely complex to do this, but it's made of almost 800 segments, each is 1.5 meters wide. You see a photo here on the side. And this poses, of course, big, let's say, big issues. You have to coordinate all these mirrors. So each of these mirrors has a lot of sensors to know how far is from the nearby one, how it's tilted, how much pressure you are posing on it, and so on. And you have to coordinate all these segments at a frequency of 500 hertz. So basically, every second, 500 times, we are moving each of these or checking, not necessarily is needed for moving, each of these segments. Counted besides obvious things like, I don't know, gravity on planet, which is pushing down things. There is also things like wind, or depending on the position of the telescope, you may compensate differently the forces and so on. So it's a pretty tough work to be done. This telescope is composed by 5 mirrors. Basically, the biggest one is on the underneath. This is the 39 meters. Then the lights get concentrated to one on the top, which then goes to another one, which can, for example, do some changing of the light path, depending which instruments you want to go and so on. And which is the most interesting of them is called the 4th mirror, the M4, which is the mirror that does all the adaptive optics. What is this? Basically, since we are on Earth, we had the atmosphere. You can imagine it's turbulence, there are winds, there is stuff on it. And nowadays, by deforming the mirror, we can render the effects of the atmosphere null. So basically, we can get the same results as we were in space, because we are, by software and by deformation of a mirror, compensating for what the atmosphere is doing. How is this done? We shoot lasers in the sky. We know which is the shape the laser should have. And then we compensate by deforming the mirror until we get the shape we expect. And then we know that the whole field of view is corrected. This is already done in smaller telescope, in the VLT I was mentioning. Here will be done at a totally different scale. Just to go in a bit in detail, This is the size of the telescope. So on the left is a representation of the ELT. In the middle, the current one. So you see basically it's covering the whole complex of the other one. And it's a comparison, realistic, with the scale of the Colosseum. So this gives you the idea of how huge the structure is. On the right side and on the bottom, you can see some comparison with the Hubble Space Telescope. So imagining an object that you can see it in that resolution with the Hubble. In the middle is the James Webb Telescope, which was a lot in the news. It's still a huge improvement. And in the third column, you can see what will be ELT with Mikado, which is one of the instruments which does also the correction for atmosphere and so on. So you can see that actually, when you talk about astronomy, size really matters, because the bigger the telescope, the more light you collect, and so the more details you can actually see. That's why it's very important to have big telescopes. Underneath is very similar, but compared between our current telescope with AEO, so with the corrections, and what will be in the future. So now I pass to Piotr.
Hello, my name is Piotr, and I will try to describe what is the role of our team in the project, and how do we use open source software and especially AlmaLinux to achieve our goals. So we are a team of about 50 engineers who are responsible for control software of ELT. Where the control software is real-time system that coordinates all the subsystems in the telescope. As Federico mentioned, one of the most important subsystems is the one that is responsible for M1 mirror alignment. M1 is composed from 800 separate segments, and they are equipped with sensors and actuators that control the position of the mirror. And here, the system must to keep the surface smooth enough that the maximal error possible is 50 nanometers, and 50 nanometers is the size of the smallest viruses we have on Earth. The other important part that control system does is control of the rotation of the dome structure, and the dome structure is this spherical building we see here in the top right corner. We had a bit of luck when this photo was taken, because it's also done before the doors were mounted, and inside the telescope, inside the dome, we see something which we call main structure. And the doors itself, they are also controlled by the control software, responsible for opening and closing the door. That sounds easy, but that's an interesting fact. One panel of such door weighs around 600 tons. So to make it easier to imagine, it's about 400 cars in European standard. I guess in US it will be a bit less, because you have a bigger cars there. But it's still quite a big parking lot of cars. The whole dome weighs about 6,000 tons, which together with doors, and the main structure inside is a bit lighter. It will have 4,600 tons together with mirrors. The main structure inside also has to rotate horizontally as the dome, and it has to rotate vertically to control the altitude. And as an interesting fact, the smaller sibling of ELT, VLT, also have pretty big main structure that has weight of 350 tons, but it moves smooth enough that one person, by pushing it a bit harder, is able to rotate it a bit. And I hope, I don't know if it will be possible with ELT as well. So all these big structures has to be controlled together, and they must be able to precisely point and track objects on the sky. And this is controlling such a giant is already a big challenge. However, in my eyes, the technique that Federico mentioned, adaptive optics, is even more impressive, because here this atmospheric distortion are a big problem in ground-based optical astronomy. And thanks to the fact that we have a technique of adaptive optics that is able to deformate the mirror that compensates the distortion from the atmosphere, the images can be way sharper. So usually it works thanks to the fact that near to the objects we observe, we have a bright star, and we know how this bright star should look like. And the adaptive optics algorithms are able to compute what the shape of the mirror should be to get the star that we expect. However, the problem starts when we want to observe something that doesn't have a bright star nearby. And in such a case, another technique mentioned by Federico was invented, which is shooting a laser into the sky, into the upper layers of the atmosphere. And this atmosphere then starts to glow, and this glow can be used as a reference point for the adaptive optics system. And what is impressive in ELT is that ELT will have 6 such laser guide stars. It will also have a hard real-time system that controls this deformable mirror, and the system has super tight time constraints. Federico is one of the persons who work in the team that built the system. It's called Wavefront Sensor RTC team. They use quite powerful AMD EPIC CPUs to do the computation. And for me, the mind-blowing thing is that when they do computation, they have to do it all within the CPU cache, because the first time they reach memory, it's already known that it will take too long, and they can't fit the constraints of the time. And then maybe as a side note, the interesting thing when telescopes are constructed, how many different fields are needed. So those laser beams are considered to be danger for air traffic. So there has to be another system that actually disable those beams when an aircraft is spotted in the field of, or nearby where the observations are done. And the last subsystem I would like to mention are instruments. So instruments are tools attached to telescopes that collects the light and analyze it. Maybe in other words, the telescope is responsible for gathering the light from the object we would like to observe, and instruments is responsible for changing this light into scientific data. And here on the picture in center, we can see a main structure of the ELT, and we can see rendered image how instrument will look like. In astronomer slang, this place is called Azimuth platform. And if you look carefully, you can maybe spot a person that are walking there around, and they are there to show how big the detectors will be. Of course, it's nothing impressive for certain people, but in astronomy, these are giants, especially in optical astronomy. So, and a bit similar like CERN, we don't do those instruments ourselves. They are done by consortia of universities and science institutes around the world. We collaborate with them on design and technologies used. They also use our frameworks and software, so it puts us in the position that we have to distribute software to consortia. And one way how one of our colleagues describes how you can easily think about this type of telescope is to compare it to DSLR camera, when telescope is a lens and instrument is a body. And unlike photographer, which usually has one body and many lenses, here astronomers have one lens that doesn't change doesn't have any major changes for decades. But the thing that changes are instruments that they can be improved together as technology improves. Okay. Yes, sorry, I have a bit of trouble to control the telescope and now control the slides. So this puts us to the moment where we can tell why open source is crucial for us. So the thing that our telescope lived for decades makes proprietary software way less usable. So many companies that produce software may not exist for that period of time. Some may decide that it's not worth to maintain a software that we use on the telescope, and open source gives us a way. It's not easy, but we can maintain software ourselves. We can fix bugs if needed. We can port to the newer operating system if needed. So it gives us a bit of freedom and make the telescope maintainable. The other important part is that cost is way more predictable. So it happens to us more than once or even more than twice that we bought a license for the software, we integrated it into the system, and then the price skyrocket because probably the selling person or the vendor know that getting it out would be too costly. And with open source, we don't have such a problem. The other very important part to use open source software as a base for the telescope is that we have to collaborate with consortia. We have to deliver, maybe not deliver, we have to distribute software to them. And in the case our framework are based on a proprietary software, in most cases license doesn't allow us to distribute proprietary software to different organizations. They have to, and they are composed from many other organizations, and each organization would have to acquire the software, their own channels, which reduce frictions. And by using open source, we just eliminate them because we are allowed to distribute open source software. License allows this. For me personally, using of open source is important because I can avoid bureaucracy. Unfortunately, at ISO, bureaucracy is a king. In case I would like to get a license for some proprietary software, I would need to first ask for an offer, then find the project that would like to pay for it, get the project manager approval, get IT department approval, get my head department approval, and at the end, I would need the approval from the finance check. And once I get all of this, the purchase order can be created. And this doesn't guarantee that I will get the software because the process can take that much time that the offer already will be expired. So with open source, I don't have to ask anyone. I can just try and check if the software fits me. And of course, last but not least, working with open source is just fun. Okay, let me tell a bit what exactly our team do. So me and Federico and also a few other persons there. We are making a Linux distribution for control software. We call it ELT Development Environment, or ELT Devenv in short. At the moment, it's a customized base distribution. It was at the beginning CentOS, then Fedora, then AlmaLinux. At the moment, AlmaLinux as the latest release. During that road, we realized that customizing distribution is not the best way. We would rather prefer to extend the base distribution, so be kind of Apple for control software. But yeah, we are not yet there. We are heading this direction. So what I'm very proud, we are very close to be 100% open source. Sorry, microphone. All our third parties are 100% open source. The only proprietary software we ship is our software, and we have decision that it will be open source. The only part is that we didn't do a homework. We didn't put proper licensing information. We didn't put proper copyright information in the files, in the sources. Once we do it, they will be also shipped as open source. So hopefully, if we meet next time, we can say that we are 100% open source. And then this may be interesting. All the control software of ELT is written in C, C++, and Python. We use a niche tool for a build system called WOF. And if someone knows WOF, I think I owe a beer that person. We write set of tools. Is there anyone? No. We write set of tools that help work with WOF. Like for example, the improve way how you can work with protobuffers, how you can work with tools like FastDDS. And as for GUIs, we use Qt framework. And in ELT control room, KDE will be the desktop environment used for controlling the telescope. And of course, there are challenges with using open source. One of it is that we sometimes get a question if AlmaLinux is supported, and this is not easy to respond because support has so many meanings. And I find this certification effort quite good because this helps with such questions. Then there are way more dramatic things than support questions. Sometimes it happens that there are changes in the licensing of the projects we use. And this happened recent years to HashiCorp, who license all their, I don't know if all, but most their tools to non-open source license, to BSL. And some of them were forked and new projects were created. But some of them we use, like Nomad and Consul, weren't, and we somehow stuck with older open source version, and we're thinking what to do with it. And also there was a problem with licensing Redis, and here are big thanks to Roberto and Jonathan for all the work around Valky, because this allows us to switch to Valky and don't worry about Redis anymore. Okay, the other problem we hit with open source is that projects get abandoned. It sometimes happens when we use a project that has one main contributor, and then it loses interest in maintaining it. But this is not a big issue, because if that happens, usually we are able to maintain it ourselves, or even fork. We haven't forked any yet, but we are close. But it's way worse if there is a big company that has a very important open source project, and at some point they change their mind. And the example of such behavior or such accident could be Red Hat, who endorsed first CentOS team. They acquired the project, and after a while also they somehow made CERN convinced that this is the best way to go and to use CentOS. And then when they managed to do all of this, they said, I think we have no much interest in maintaining CentOS, let's go do CentOS Stream. And this was a huge punch for us, because we spent the summer before with Federico to port our development environment from CentOS 7 to CentOS 8. And in autumn or winter, we get the message that all the work was a bit useless. But like all challenges, there are also opportunities to grow, because it forces us to think a bit what to do next. And we realized first thing that we are between a rock and hard place, because we have two types of users. One of them is very conservative. They would like to have the distribution that is very smooth updates, that they don't have to worry about updates because they can focus on their complex systems. And we have also the second type of developers that are early adopters, who says that we build telescope for the future, and why do we have to integrate against versions that are already old and not maybe still maintained, but old, and would be much nicer if we integrate against newer versions. and both of the sites have some kind of right. So and at the end we made a decision to that from now on we don't decide about the version. We use the version from upstream. So it's only no developer or no us can decide. We use what upstream gives, and this made our work way easier and also the quality of our environment way better. And let me say why. So one thing that end of the CentOS Linux was for us opportunity to grow, but it was also opportunity to grow for AlmaLinux. And as Andrew said before, with CentOS we had releases after around a month, while with Alma I think there were a few that were the same day as RHEL, but usually there are a few days later, and for now maybe always 6 days later. We also value very much the fact that Alma decided to be ABI compatible instead of one-to-one rebuild, because it opens a lot of new opportunities like support for the old hardware. And we had a lot of servers in ISO that has Megabyte, which put us a lot of headache that RHEL removed it. Yeah, and let me just mention how do we build our environment. So it was quite adventure to go through all the tools we used, but at the end we started to use open source open build service, which the biggest advantage is that it triggers rebuild automatically. So for example, if any package change from Alma or from us, it knows the dependency tree and is able to trigger rebuilds. Yeah, and let maybe Federico talk a bit about ISO contributions. I guess this will be one of the last slides because he's one that contributes the most in the project.
Very short, since we are already out of time. Sorry for this. So as ISO, we have some software, but it's mostly scientific, which was released under GPL from many years ago. Maybe you heard about this, but if you are not in astronomy, maybe not. And as Piotr said, we are going to release. Some parts are already there, others are still to be redefined. All the ELT software as GPL version 3. Of course, I'm not expecting that people will use the telescope-specific stuff for their home appliances, since, as we said before, there is not much big telescopes, but there are also some interesting bits. For example, for the HRTC, we have libraries that do specific things very optimized. I don't know, Locklex Q and things like this, which you maybe find of interest, or some optimized communication. We try to give as much as possible back to Fedora, Apple, or Alma. So me, Piotr, are also Fedora packagers. We maintain quite some packages and try to put to Apple, especially what was not there yet and is in Fedora. And we try to also contribute back bug fixes or whatever we find. Of course, whenever we find something, we also try to do upstream first. So we try to send all this as soon as possible upstream, and we have a lot of contribution in this project that you see here. Last, if you are interested in astronomy in general, you can find here, it's not moving anymore. Okay, here, the Science Data Archive, as I said, all the observations are public. So whatever our telescope look at is available to everyone. You just go on the website and you can find everything there. There is just an initial period, which is dedicated to the PI, which is the principal investigator, whoever proposed to watch that. So he can do some specific science and, if applicable, get the Nobel Prize for that. But then after some time, which is usually 1 year, everybody can do. You can go there and you can search for life or whatever you want to do with it. On the links above is more pretty to see stuff, which is basically images and videos, also full dome planetarium, which are released under Creative Commons and gives you the possibility to do this in public. We don't have time for question, I believe. We had a frequently asked question, which I will go through extremely fast. So we are often confused with ESA, which is the space agency. So I always get the question when we are going to Mars. We are not going to Mars, but Chile, Paranal, where is our observatories, is pretty there. So you see a comparison between where we observe and real Mars photos, and actually ESA comes to Paranal to do tests with the rovers often. The second question is, of course, if there is life out there. I cannot confirm nor deny, of course, but you can see that just behind the telescopes, that is LaCie telescopes on the top, there are these petroglyphs, which are incision of stones, which date between minus 200 before Christ and 400. And as you can see, some are pretty much interesting. I don't know, they can tell you something. It wasn't me doing that, they are really there and they are original from a long time. Last but not least, when you talk about astronomy, of course, everybody thinks that you are into astrology, so you get these kind of questions. And I can't really help with that, but maybe after some beers, and this is from FOSDEM actually, we recognize the Belgian beers, maybe we can be of help, but not, at least not officially, so out of working times. So thank you very much. Sorry we went late. Here is a photo when ALMA team came to visit us at ESO about a year ago. Thank you for coming. Thank you for presenting to us. And thank you very much to everyone. You can come to visit us in Chile if you want, if you are nearby, or much easier in Munich and the planetarium. Thank you.